SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 4, that is Hydro and Renewable Energy Generation Systems. So, in our last lecture we are covering the energy harness mechanisms from oceans. So, part 1 we have covered, where it was emphasized that ocean temperature difference from the ground and the deep water will give the significant impact for harnessing energy through heat engine principle. Now, moving further, we will now in those context, it was the groundwater and the deep water that gives the necessary temperature difference through the concept of heat engines. Now, in this lecture we will be focusing on waves, because in earth around 70% of space is being occupied by oceans and seas, and almost everywhere or in most of the geographical sites we will find waves and tides. So, both are actually governed by the gravitational forces of sun and earth on the surface. So, because of this reason, since there are some waves, so those waves have significant potential to harness energy or power. So, in this lecture today we will be focusing on harnessing energy from oceans. We will mainly focus on ocean waves, energy and power from the waves and wave machines, and also will focus on tidal energy. This tidal energy comes by virtue of lunar cycle on or effect of lunar cycles on water surface of sea and ocean. So, just to give insight in our previous discussions, the solar energy is the main source behind this formation of various renewable form of energy on earth. So, if you say solar energy as renewable source of energy, first type of energy that we get in passive manner is due to uneven solar heating on earth surface, that is on earth surface. So, we call this as a wind energy. And when the solar energy is absorbed by the seas or ocean surfaces, then it creates currents within the sea and ocean, and this current, and due to this current there is a circulation of water from ground, from the surface to the deep water. But however, most of the cases the deep water does not get the impact of ground surface water when you see beyond the depth of 1 kilometer. So, for that reasons there is a definite potential of the temperature difference that is available from the deep water and the surface water, and that difference is close to about 15 degrees centigrade. So, when you harness energy or power output through this temperature difference, we call this as ocean temperature energy conversion. The next part of solar energy as a passive impact is rain. So, when the solar radiation comes on the surface. So, water get surface of sea or ocean, water gets evaporated and moves up, and they form cloud at high altitudes, and ultimately or eventually it comes as a rain. Now, when this rain comes, we collect this rain water in dams or hills or high altitude area, and through this we get this hydraulic energy, and this hydraulic energy is by virtue of potential energy of water which is stored in a dam. And next part is the tidal energy, and this tidal energy is mainly occurs due to the gravitational effects of lunar and solar and lunar cycles on the ocean surface. So, our main intention in this lecture is about this tidal energy, and also to some extent if we say that when we have a waves, sea or ocean waves that comes in the coastal area, there also there is a possibility to harness the energy, and that through some machines what we call as wave machines. So, the focal point of our main attention for today's lecture will be the tidal energy and ocean waves. So, I mentioned some of the most significant impact of renewable energy, and on top of that wave energy also falls under that under that category in renewable form. Although this infrastructure cost is very high, but they have a good potential because they are available free, but we need to have a particular geographical site to harness those energy, and we call this as a wave energy. So, there are some advantages because they are alternative form of energy and they are freely available, and they do not require large land masses because wherever the coastal areas, they can be considered by default as the area in which we need to install our device. But main disadvantage is that these wave energy instruments or devices are to be kept in the site itself. So, at the time of large wave activity or in case of unforeseen circumstances that like storms, cyclones, so those machines has to take care about its sustainability. So, mechanical strength to withstand that enormous power in stormy sea areas is a big issue. Another is capital investment, maintenance cost is very high and sometimes it is not known to us. So, this makes some kind of a negative impact of wave energy, but still a technical viewpoint it has a great deal of capacity, because almost in earth 70% of the area is occupied by seas and oceans, and we can have coastal area belt as the main basins for to get the tides or waves. Now, before we go further, let us try to understand ocean waves, and for that we need to know something about this wave motion. So, what happens in these coastal areas, you will find a kind of a progressive waves that comes from the that comes to this in these coastal areas, and these waves take the pattern of a sinusoidal pattern, and what we have taken one particular segment in which a wave is defined, and this wave has some specific characteristics. If you take a sine wave like this, then we have a there are topmost part of this wave, we call this as a crest, and height from this mean line to this topmost position is known as amplitude of the wave. And when this waves comes in the bottom part, then there is a trough, that means it also gets negative peak in terms of a. So, through this process we get a wave height of 2a, and of course, that is for a given wave we also define a length what we call as wavelength. So, the periodic fashion continues in certain time, and that is called as wave period. And once this wave period happens, same trend of the wave continues. So, this is a very sequential wave, that wave starts at this point. And if you look at a phase rate, that means same wave, but if it does not start at y is equal to 0 or x is equal to 0, but it start at some other location. So, there is a phase rate in terms of its vertical axis. So, that way the waves are characterized, and now this is what we see the wave at maybe time t theta is equal to 0, but at a different times the waves may take a different phase. So, those are the significant ways we characterize this wave. Another important parameter is the frequency of the wave. I mean, what frequency the wave continues, and that is nothing but the 1 by time period, 1 by tau. We also defined the wave velocity c, and this wave velocity c is, that means the how the wave progresses in x directions. Now, having characterized these waves and taking the statistical data in standard seas and ocean, it has been found that there is a definite relations in terms of water depth. That means, if you are going deep into the sea water or ocean water, starts with 0.3 meter to let us say 3 kilometer depth, and you see this visualize this wavelength, let us say for one particular wavelength lambda, we find that there is a specific wave period. Now, for another type of wavelength, this that also have specific time period. Now, if you keep on doing it, and peculiar characteristics follows from this data. That means, if you draw a line, inclined line, and one particular things that we see is that with water depth below 3 meter or 30 meter or 300 meter, we will find the wave period and the characteristics feature of this wavelength, and this wave period is almost remains same. Now, looking at this, one can find a relationship between wavelength and period, and that we are going to emphasize here. So, to characterize this wave, one standard way to write this expression of the wave is y. Y stands as that if you take the mean line at any location y, at any point on this wave, if you take this vertical line, we say it is a y, and at point we can frame these equations y is equal to a times sin twice pi by lambda x minus twice pi by tau into theta. So, simplify it gets, it is written in a simplified manner like y is equal to a sin m x minus n theta. Now, when this m and n are defined in this manner, and of course, we have this wave velocity c is nothing but, if you know lambda and this wave period, we can find the wave velocity. We have this value m and n just to simplify this sinusoidal expressions. Now, from this data, one typical relationship that is obtained is lambda is equal to 5.12 tau square. So, that means, if you look at a water depth of 3 kilometer or more, we will find the wavelength relations in terms of wave period and tau square multiplied by 5.12. So, based on so this is what the characteristic pictures of at any geographical location and at a particular depth, the characteristics feature of wavelength and wave period. And of course, we have definitions of frequency, and we also define this phase rate. All these things can be defined for a particular wave. Now, once you say this wave, so we look at this wave, these two dimensional waves mostly in the coastal area. Now, the way we see the wave, that means it is not it does not replicate the water motion. It is the wave which is the characteristic features of the pattern that is followed by slug of mass of water, but each water particle does not follow the sinusoidal pattern. So, that is the characteristic features that the motion of the water is not in the sinusoidal pattern. So, in reality what happens, a given particle of water rotates in an elliptical path in the plane of wave propagation with specified horizontal and vertical axis. Now, when you say ellipse, it has a major axis and it has a minor axis. So, you define this elliptical path as semi horizontal semi axis of the ellipse and vertical semi axis of the ellipse. Now, what happens, because we see this wave not exactly on the surface, it also there is a depth. So, if you look at depth, you take a particular bottom of the surface as depth and measure this height to this mean level of the surface wave, we say it is h, and any location we say it is a eta. So, basically entire height is covered with a sinusoidal wave, but the motion of the water particle is mostly elliptical. So, let us say when you say when looking at that wave at this on the surface, it has a elliptical path which major axis alpha and minor axis beta, and you say this is the mean level of the wave. Let us say from this ground, if you say this is the mean level of the wave, and this is how we look at the things. Now, if you keep coming down towards the depth from the surface, then slowly we will find the elliptical pattern is going to change to circular. So, that means at the bottom of the wave the pattern is mostly circular. Why we say this? Because you will find that the semi axis, horizontal axis and vertical axis, that is alpha and beta, they they approximately alpha becomes approximately beta, and that is nothing but the A. A stands as amplitude of the wave. So, that relations makes the conclusion that when you look at the same wave at the surface, it is an elliptical, and the same as wave in the bottom, it is a circular. So, that is the pattern there the waves follow. Now, through this pattern of the waves, let us see, because we are interested in harnessing energy from the wave, but these looking at these wave parameters, the energy numbers has to be calculated. Now, for that there are two types of energy and wave possesses. One, potential energy that arises from the elevation of water from the mean level. Another one is the kinetic energy of the wave, which is the energy that liquid between two vertical planes perpendicular to the direction of the wave propagation placed in one wavelength apart. So, if you look at one particular wavelength, that means starts of the wave, end of the wave, within that wavelength we see that whatever energy that the water particles or slug of water possesses by virtue of its velocity, and this velocity of the wave we know it is c, and that also can be related with respect to amplitude and wavelength. So, we are not going into deep into this theory. So, there is a hydrodynamic theory that tells us that what is the kinetic energy and potential energy that possesses by the wave. Now, here we are looking at a arbitrary length L in a two dimensional plane, but along that arbitrary width we are looking at a wave having wavelength lambda. So, basically if you say it is the wavelength lambda, so this height or this width is normally called as L. So, within that area let us lambda times L, that is your wave area, and we are looking at what is the energy which is being possessed by that particular slug of water mass. So, that way we can find out the kinetic energy and potential energy per unit area, and it happens to be the fact that both are equal. Kinetic energy per unit area is 1 by 4 rho a square into g, and potential energy is also rho a square into g. So, by adding these two terms we get the total energy per unit area half rho a square into g. So, g is your of course, it is a acceleration due to gravity, and then from this if you know the frequency of the wave or what occurrence the waves comes into pictures. So, time also gets included here. So, the energy term can be converted to power term. So, power density per unit area also can be find out by multiplying it with frequency, and this in fact gives the total power density of the wave. So, once you have estimated this, we can say that at a typical location we can estimate this number to be 840 watt per meter square, that is power density of the wave in a particular geographical locations. But same thing if you compare the solar at a particular location, it is 240 watt per meter square. So, here you can see a significant difference, although the ocean waves are gets generated due to solar radiation, but intensity or power density of the wave energy is much higher than the intensity due to solar energy. So, it gives a significant impact that density of wave power is about 3.5 times higher than that of solar power. Now, once you know the estimates of the kinetic and potential energy wave, let us see what is the technology behind to harness this energy. So, for that one simple device is called as float type wave power machine. So, essentially what does it do is that it is a wave machines that harness wave power, and here while harnessing, it is harnessing by storing air in a tank, and this air we call this as a air storage tank. This air storage tank is further connected to an air turbine, and that means this compressed air is gets expanded in a turbine to generate electricity. So, what happens whenever that wave energy is available, we store them, and this stored air or high pressure air gets released for the power generation or the subsequent method by expanding in a turbine. Now, to store this energy in a tank, what we have is a device called as simply a kind of a piston cylinder device, or you can say it is a compressor, and this is put on a float. Float means it is like a device which normally floats on water. Anything that floats is a, you call this as a float, and that normally float, and here this float means it floats in the wave. So, wave has a series of sinusoidal pattern, and during one case we can say it is a compression, other case it is we can say expansion. What does it do is that when the float is there, when in one slug of means one path or in one period of the wave, the piston gets compressed, and whatever slug of air that is there in this cylinder is then compressed, and the store gets it enters in this path and finally enters to the storage tank. So, this is what we say piston's compression stroke. So, now when the piston is in expansion stroke, that means when the piston comes in the expansion stroke, air from the atmosphere sucked into through this inlet valve, and this happens in the other cycle or other part of the wave. That means one is crest part, other is trough part. So, during crest part the piston sees a compressions, and in the trough part piston looks as a expansion. When it is in expansion, the atmospheric air enters into the cylinder, and during the compression part the stored energy gets into this air storage tank, and finally these air storage tanks they are integrated to with an air turbine. So, this is the mechanism that we get power from the wave. So, since it is a kind of a simple reciprocating device, one can frame the pressure volume diagrams. So, if you see this particular wave, and this is the float position, and we have the wave height 2a. So, since instead of 2a, the stroke length will be little less than that, because the float has certain width or or height. So, effectively we have the stroke of the piston. So, initially we have atmospheric air conditions at P 0 and B 0. So, atmospheric air gets compressed during the compression stroke of the pistons, and the final volume becomes V 1. Now, at this now during this compression, and we call this as a polytropic compressors, P v to the power n is equal to constant. Now, during the compression, obviously temperature gets increased. So, effectively we need to bring down these temperatures in an isothermal process. So, from this point you go along an isothermal line, and finally we have the your final volume will be V 2. So, basically keeping pressure P 2 is equal to P 1, we arrive at the new volume, because we are cooling down from state 1 to state 2. So, finally we arrive at the expressions when you get the work done by the turbine. That means, after this compression the air gets expanded in the turbine. So, work done by the turbines is a function of some non-dimensional number, that is RC, compression ratio, or RC is the pressure ratio in the compressor, RE is the expansion ratio, then we have P 3 is the exhaust pressure from the turbine, RC is P 1 by P 0, RE is P 2 by P 3, and effectively this RC by RE is in the order of 1.1. So, these are the numbers, realistic number that we get. So, we are not going deep into this calculations here, but that is the end results that we get, the ultimately how much power we can harness from a wave. So, one, and like in our previous discussion I told it is a float type wave power machines. So, what happens in a float type wave power machines, we are using the power of the wave or energy of the wave to compress the air in a storage tank. So, basically water power gets converted into gas power in terms of air. But there are some wave machines or devices. So, instead of storing air, they store water itself in a very compressed form. So, high pressure water gets compressed, or we say water storage machines, and those machines are called as hydraulic accumulator wave machines, high level reservoir wave machines, or dolphin. That means, you take that wave and store that water at certain level height. There is a dolphin type wave generator, dam atoll wave machines. There are a variety of machines that takes care about the storing water instead of air. And one typical example I can cite is that for a float size of 3 into 1 meter and 0.5 meter dimension, if you have this float dimension of this sort, and this of course an experimental evidence that at a given location, if you say that wave amplitude is A and wave period is tau, then one can find out for this wave machine or which is normally run through storing water, we can get the power per unit length perpendicular to the wave follows a relation, that is P by L is equal to 1.74 A square into tau. So, this is the expressions that is a what we can say experimental correlation for a given geographical locations. That can be more or less an estimate that how much power we can tap. Then next segment of our discussion is the tidal energy. So, basically here we say that when you say wave energy, it is a continuous process, it is throughout the year, and it is mainly due to the combined effect of solar and moon cycle. But there are some situations when you have tides. Tides are mainly governed by lunar cycle, and these tides are very frequent in at some particularly geographical site. And why we say tides are these things, because the tides have very significant impact in some period of moon cycle. There is a tides are very high. So, if you look at particular lunar cycle which falls as a 29.5 days period, we can see very high tides and low tides, and they have significant difference in their height. So, if you draw a mean line, we can say that the difference between the high tides and low tides, and that we call as a tidal range, and occurrence of the tide happens to be in a periodic manner governed by this lunar cycle. And what happens if you take a 29.5 days period, and one wave period will be about 12 hour 25 minutes. So, this is a pre-calculated or effect of how the effect of moon position on earth surface, what you see moon on earth surface, from the earth surface. So, it starts with a new moon, go to the first quarter. So, we will have a low tide. So, when you have a new moon, it is a high tide, and we say it is a spring tide, and when it is a low tide, we say neap period. Again during spring period, tides we say full moon, and again that means tides are very high tides, and the cycle pattern continues in 29.5 days periods. So, this picture gives relative tides during a lunar month. Now, why these tides are occurs? Because this is mainly due to the gravitational force of the moon and sun acting together on earth's centrifugal force on water. And why it comes? Because it due to the earth rotation. Now, the net result of this rise and fall of water is not constant. So, they are characterized by schedule and range, which is defined in this manner. Range means it is a height, schedule means it is a time period. So, thereby we have the virtue of having very large tides which is close to 20 meter high, which means these tides will can have a significant impact for energy harness. Now, let us see that how we can tap this tidal energy. So, to tap this tidal energy, we need to think about a single full tidal systems. So, what happens at a given geographical site locations, you create a dam which is something like this, and we also know that when you create a dam, we will see that in some period this side will have high tide, other side will have low tide, and in some other period will have reverse also. So, basically that means high tide and low tides can be reversible on both sides of the dam. And when you say it is a dam, essentially speaking, that during the high tide period, that means one side will have a high elevation of water, and that elevation of water can go up to 20 meter height. So, during the other side of the period, it is a low things. So, we can operate a reversible turbine which can operate in either side and to or it is like a water turbine and to produce power. Now, this is something like integrating a hydro electric dam in a particular site locations for tide. Of course, this potential height is not that much high what we normally see in the hydropower plant, but it is quite effective to harness the tide power. Now, what you see in the water level with time, because time stands as is the schedule. So, water level positions, there are two parts, one is the pattern that tides that follow, other is the pool level or ocean level. So, pool level is nothing but your one, there are two sides of the dam, one is it is a single pool. So, that means there is only one side, it is we store the water, other side is the water is less. So, difference between these two is your range. So, that is effectively what we say for a given tide range we will find this is the range. So, that range could be as high as 20 meter. So, effectively this 20 meter height potential energy can be harnessed. Since it is a cyclic process, we cannot have a continuous power because water level keeps on changing with time, and a simplified model can be a triangular pattern, but we can that means power versus time curve will be a triangular pattern. So, it is a continuously up and down, but we can have a minimum kind of average power that can be calculated for this range R. So, a typical mathematical expressions can be given from this graph. So, we have pool level, we have ocean level, and this we have this generation period 6.2083 hour. So, how it comes? Because we see that the power generated during one tidal period is 12 hour 25 minutes. So, it occurs once that means this is 6 hour 12.5 minutes. So, it is close to this number of hour or this many seconds. So, simplified expressions for work done from the water is nothing but mass rho g h. So, if and here we will see rho is your density of water. So, it is a sea water, it is a constant. H is also a relatively height is same, height does not change because we know for a given location lunar cycle the typical height of the tides. So, what changes is the mass, because the change in the mass is frequent here. So, this mass we can write it as a dm. So, dm we can write it as mass is density times rho g h. So, that term density term can bring into picture. So, we get a differential work, and that differential work can be integrated for this entire height range, and this turns out to be that is theoretical work obtained for a single pool tidal system is half g rho a r square, where all these things are known, area is known, rho is density, g is the acceleration due to gravity, r is your range of the tidal range. So, this is what the r is known. Now, we know this time period, that is 6 hour 12.5 minutes. So, from this work and time we can calculate the average power. So, effectively that number turns out to the fact that average power density for a that we get average power, you take area in one side. So, we get an average power density, that is P average by A. So, this effectively reduces to a very simple term average power density for a single pool tidal system is 0.225 r square. So, this is a very significant observations that we get, that means we can say the capability of tidal power at a given geographical locations. And some other important inference that we can say that although we get those numbers, that is the capability of tides in a given locations, but the average efficiency is in the range of 25 to 30%. So, one simplified analysis can lead to the fact that if you take an average area of 13,000 kilometer square, that means you take a coastal area and we spreads about 13,000 square kilometer, and where the tidal range is availability is 8 meters, then for this area and this range the capacity of tidal power could be 50 gigawatt, and this is again with an efficiency of 27%. So, you can imagine that how much large power is possibilities or capability of tide power in a from the sea or ocean resources. This number is huge, but the infrastructure or harnessing them technology is the more challenging. So, okay, with this we come to the end of this lecture. So, we will try to look into some of the numerical problems that we covered in this lecture. So, the first problem is on a oceanic wave which is of 2 meter long and it has wave period of 6 seconds and it occurs at a surface water depth of 100 meters. So, you take a particular 2-dimensional progressive wave and this characteristics feature of the wave which has given to us is its length is 2 meters. So, you can say it is 2a is 2 meter. So, 2a stands as from crest to top distance. So, that this will give you a is equal to 1 meter. What other things has given? Tau has been given as 6 seconds. Depth of water which is h is given as 100 meter. We need to calculate the other features like wavelength, wave velocity, horizontal and vertical axis of water motion. So, this is wave motion, this is water motion. So, other feature first thing we can say is what is the wavelength relation with time period, that you recall our expression lambda is equal to 1.56 tau square. So, tau is given 6 seconds. So, this is 56.2 meter. Then wave velocity c, that is equal to lambda by tau and this is 9.4 meter per second. Then we require we also need to find frequency is 1 by time period, that is 1 by 6 hertz or 0.16 hertz. We recall this is about wave. Now, about water motion, we can see the water motion is mainly elliptical in the surface and it is circular in the bottom. Bottom means this height is given to us as 100 meter. So, what we need to recall from our analysis, that is major axis of the ellipse which is alpha, that is equal to a times cos hyperbolic function m into eta. So, eta is measured distance from the bottom and that is divided by sine hyperbolic function n times h. So, m times h. So, what is m? That is equal to twice pi by lambda, that is twice pi by 56.2. So, putting this number we write as 1 cos hyperbolic twice pi by 56.2 into eta. So, eta water motion at the bottom, because we have given height for the bottom and that is at 100 meter, and then that is sine hyperbolic 36.2 into 100. So, if you calculate this number, this is also 1 meter, that is the cos hyperbolic and sin hyperbolic remains same for this number. And similarly, minor axis beta is given by the expression of a sin hyperbolic m into eta divided by sine hyperbolic m into eta. So, putting this number we will have, this is also 1 meter. What it demonstrates is that alpha is equal to beta is equal to A, which means circular wave at bottom, and in this case that is h is equal to 100 meter. This is what exactly a standard wave follows, ocean wave follows. Then we can find out the energy and power density. So, energy density, that is E by A, is the expression half rho A square into G. So, you take this density of water rho as 1025 kg per meter cube, that is typically saline water. So, putting this number 1025 A square 1 square into 9.81. So, this number is 5027.6 joule per meter square. Similarly, power density P by A is equal to, is nothing but we know E by A into frequency. So, 5027.6 into frequency is nothing but in this case it is 1 by 6. So, it has power density is 837.9 watt per meter squares. So, this is the power density for that wave, and from this wave if you want to harness, if you use a float type wave machines, we need to find what is the power per unit length perpendicular to the wave. So, that expression we recall, that is what is called wind power per unit length P by L. So, this is a experimental observations, that is 1.74. You can use this relation A square into tau. So, that is 1.74 into 1 square, tau stands as 6. So, power per unit length is 10.4 kilowatt per meter, because this, for this relations holds good, power is in the kilowatt and A is in your meter, tau is in the seconds. So, for this wave machine we can get this many power. Then we have this next problem, that is on tidal energy. So, tidal energy we look for a single pool tidal systems, for which range is given as 12 meter and pool area is 10,000 kilometer square. So, for that things we recall our expressions, this theoretical work from tidal for a single pool tidal system, for a single pool tidal system. It is given by this expression W is equal to 1 by 2 rho G A R square. R stands as the tidal range, and in this case it is 12 meter. Rho is 1025 kg per meter cube, and here area is given us as 10,000 kilometer square, but we are requiring average power density. So, average power density P average by A is given by, okay, then we have this tidal period. It is about 6 hours 12.5 minute. So, this is 22350 seconds. Now, when you put it, this turns out to be 1 by 2 into 22350 into A comes here G rho r square. So, putting this number P average by A as where we have G is known, rho is equal to 1025 kg per meter cube. So, putting this number, this power is 32.4 watt per meter square, or we can rewrite as 32.4 megawatt per kilometer square. That means, watt is converted to megawatt, meter is converted to kilometer. So, this number remains same. So, effectively we can have average power is if you have 10,000 kilometer square. So, the average power could be 324,000 megawatt. So, this is average power which is available in the tide is 324,000 megawatt, but if you take, even if you tap 27% efficiency, then P actual power could be 90720 megawatt. That means, just multiply this number with 0.27, will arrive at this power. So, effectively what we say is that in a large area the power density for the tide is quite high, and if it can be harnessed suitably, it can sustain the energy or power requirement for big cities. So, this is all about my discussions today on ocean energy and tidal energy. With this lecture I conclude. Thank you for your attention.